Let's try applying this design process to another tree problem. Here's the problem. Implement smalls, which takes a tree instance t containing integer labels. It returns the non-leaf nodes in t whose labels are smaller than any labels of their descendant nodes. And here's a one-line description of the behavior. Return the non-leaf nodes in t that are smaller than all their descendants, and an example. First, the data definitions. This works directly with trees. We don't know in this case what they represent, so there's not much to do in step 1. Step 2 is to write down the documentation. Well, some of it's provided for us, but an important piece of the documentation is to know the signature of the function and the types of what arguments it takes and what it returns. Smalls takes a tree. I know that because it says so, and I also see an example. Smalls A is called on a tree. What does it return? That's an important thing to think about and take note of if you want to implement this function correctly. It returns the non-leaf nodes in T, but in what format? Well, here we see a call to smalls A is some iterable, and each element in that iterable has a label. So that tells me that smalls needs to return some kind of list or iterable over trees. So we're representing these non-leaf nodes as the tree instances themselves that live within the tree T that's passed in as input. Step 3. Work through an example. Here we would draw the diagram and try to figure out for each node whether it's a non-leaf node in T whose label is smaller than any of the labels of its descendant nodes. How about the root? 1 is not smaller than all of its descendants because it has a descendant 0. How about 2? It is smaller than all of its descendants. It's smaller than 4 and 5. How about 4? That's a leaf. I'm looking for non-leaf nodes. 5 is a leaf as well. 3 is not smaller than 0. 0 is smaller than all of its descendants. And 6 is a leaf. One important thing to note is that 1 is smaller than 2 and 3. It's just not smaller than 0. So somehow when I'm writing down the implementation of this function, I'm going to have to make sure that I know the smallest value anywhere within the subtree rooted at a particular node, as opposed to just looking at the direct children. But I'm not done working through this example. I should explicitly write down what gets returned when I call smalls on A. Let's build a list. What's in that list? Trees. So the list I'm meant to be building is the tree rooted at 2 and the tree rooted at 0. And the doc test example doesn't show me those whole trees. Instead, it just shows me the root label for each of these subtrees in sorted order. So I see there's a 0 and there's a 2. Okay, now I try to develop a template. The template is create a list, use some recursive function called process in order to populate that list and then return the list. But notice that now I've introduced a new function. And so I should go through the process again. Data definition, there's not much to do there. But what's the signature of this process function? Well, I have to figure out what it's supposed to do. I think what process should do is take in each node of the tree and figure out what's the smallest label in that tree. Why do I want to do this? Well, in order to figure out whether 1 is one of the nodes I'm looking for, I need to know what's the smallest label here and what's the smallest label here, because 1 has to be smaller than all of its descendant labels. So the goal of process, which I've discovered just by thinking about how I'm going to implement smalls, is that I need a function that tells me what's the smallest label in a tree. So the signature of process should be that it takes in a tree and tells me the number, which is the smallest label. And then I need a concise description of its behavior. Find the smallest label in T. Now, it's possible for a function to do two things. And in this case, while we're processing this node to find its smallest label, we can also figure out whether to add it to the resulting list or not. Because when we find its smallest label, that means we're going to find the smallest labels in its branches, and then we'll know whether it's one of those labels that's smaller than all of the descendant node labels. And if so, we can add it to the result. Now, in the process that I shared with you earlier, I would actually start writing down snippets of code. But let's try to follow their process instead. Their process would be to work through an example. So here's an example, taking in 2, 4, 5 as the input to process. We would compute the minimum label in each of its branches. Find the minimum of all of those in order to figure out the minimum descendant label. Decide if that's less than or not less than the root label, 2. In this case, 2 was the smallest thing. And then we have to find the smallest label in the whole subtree, which means taking a minimum between the root label and the smallest value that we've seen in any of the branches. As I worked through this problem further, every time I used the name t, I would just think about this particular example that I worked through. Now I think we're ready to write a template. The template's going to be something like, if this is a leaf, then it's easy to find the smallest label in the whole tree because there's only one label, so we'll return it. Otherwise, we need to compute the minimum of the smallest label in the branches and the root label itself. Now would be a fine time, if you weren't taking an exam, to look at the template in the question. Here it is, and feel free to pause the video at this point and try to solve it. The good news is that the template given to us is just like the template we invented when we were thinking about the problem in the first place. And so we already know what to do here. If t is a leaf, then we'll just return t.label. Now we should check this against our signature immediately. This is a number, which is what we're supposed to be returning. It's the smallest label in t. Have we accounted for the fact that maybe we should add t to the result? Well, if t is a leaf, then it can't be a non-leaf node, so we don't need to add it to the result. Otherwise, we know a t has branches. So we need to find the smallest label in those branches. If the root of t is even smaller than the smallest descendant label, then we need to add it to result. And here we see a confirmation of what we described earlier, that the return value should be the smallest label in t, which is either t's label or the smallest label in its descendants. So here I think I would do the following. I would note that I need to append something to result under some condition. And what do I append? Well, here I look at the signature of smalls and know that result has to have trees in it. So what's the name for a tree? T itself is the tree that I would add. The next thing I would do is write down what I've learned about smallest. Smallest is going to be the name for the smallest label in any branch of t, or any descendant of t. Once I know what it is, I can figure out how to use it, even if I haven't written down how to compute it yet. The condition under which I append t to the result is that t.label is less than the smallest thing in any descendant node. And finally, I have to compute that smallest thing, which is a minimization over a recursive call to process for every branch of t. Here's a familiar pattern of aggregating the results of recursive calls. And this is what allows us to process all of the nodes in the tree. We process the root, that processes the branches, which processes the branches of the branches, and so process is going to be called once for every node in the tree. And for each node, if it's a leaf, we will compute the smallest label in that leaf, which is just t.label. Otherwise, we will compute the smallest label in the whole tree and maybe add t to result as well.